So previously we got introduced to feed-forward neural networks or multi-layer perceptrons in how they work in theory. So now we want to see how we can practically use how we can use this in practice to solve problems or to specifically to classify data. So for classification, so in this video we will see how we can use scikit-learn to do this. Scikit-learn offers so the neural networks that scikit-learn offers are a multi-layer perceptron classifier and multi-layer perceptron regressor. So with the classifier we can classify data, and for with the regressor we can also do regression. Now we'll look at the multi-layer perceptron classifier that scikit-learn offers. Yeah, so here we can see what are all the parameters that we can set when we create this type of neural network using scikit-learn. As we can see, there are many parameters, such as hidden layer sizes, which activation we're going to use, which solver we're going to use to optimize the weights, some regularization parameters, the learning rate, how many times we should iterate through the training set at most, and many others. So now we'll look at each of these parameters in detail. You can read more about how to use this at the official scikit-learn website. So the first parameter is hidden layer sizes, and this parameter tells us this parameter tells us how many neurons we want to have in each hidden layer. And so the parameters that we see here are the defaults. So the default hidden layer sizes value is 100. That means that we have one hidden layer with 100 neurons. We could, instead of this, we could have one hidden layer with fewer neurons, or we could have multiple hidden layers. This parameter is a tuple, so we write the number of, and each element of this tuple gives the number of neurons in each hidden layer. So for example, if we had 100, then comma 10, comma 20, that means that we have 100 neurons in the first hidden layer, 10 in the second, and 20 in the third. The sizes of the input and output layers are determined automatically based on the data. Then we have, this parameter hidden layer sizes is one that we're going to manipulate often. Another parameter that we're going to want to set is the activation function that we use. The options that the scikit-learn offers for this are the identity function, which just returns the same value that we input. Then the sigmoid function, which is called logistic here. And we saw that on the slides earlier, in the earlier videos, what this function looks like. Then we have the option to use the hyperbolic tangent function, which we also saw earlier, and then the rectified linear unit function, which we also saw. By default, scikit-learn uses the rectified linear unit function. Then we can choose the solver that we use to optimize the weights. So we said that the way that weights are computed in a feed-forward neural network is to try to minimize the loss function, or the discrepancy between the correct outputs and the outputs that the network gives. And there are many ways to minimize the weights to minimize the weights, so that to minimize the function by changing the weights. So the way in which the weights are computed is determined by the solver here. And we have the names of the solvers that we can use. The default solver is Adam, which works well on large datasets. However, for small datasets, maybe this other solver might be better. Then we have regularization parameters. So if we want to add regularization terms, that we could also change this alpha parameter. Then again, we have batch size, the batch size parameter, which is used to help the stochastic optimizers, so we can just leave this to be determined automatically. Then we saw what the learning rate was and how it can affect the performance of the neural network classification. We can set it using the learning rate init parameter, which by default is 0.001. And additionally, the learning rate doesn't have to be constant. It could be, it could also adapt. In this case, if we fail to improve for 2 consecutive epochs, so 2 consecutive passes of the training set, then we could lower the learning rate to something else. And also we could use this other option, which will gradually decrease the learning rate at each step. By default, we use a constant learning rate like we saw in the earlier videos. Then we can determine how we want to lower the learning rate if we set it to invert scaling using this power T parameter. Then we determine how many, so we determine the maximum number of passes through the training set, or this parameter max iter tells us how many times each data point will be used. So this is used if the solver doesn't converge. That means if the solver doesn't, so if the result doesn't improve by a given tolerance, which we give in this parameter, then we will keep passing through a training set until this condition is met. So so the score doesn't improve. Or we could stop earlier. So, for example, if we doesn't reach this condition, the stopping condition in 200 iterations, then we'll stop with the classification. Then we could shuffle the samples in each iteration, which happens by default. Then we can, since this classifier has a random component in the weights and bias initialization, and also the batch sampling that we saw earlier, we could pass some random state, so some integer to some integer, and then if we want to reproduce the results that we get, so if we want to get the exact same weight initial weights as previously, then we want to pass in the same random state. Otherwise, if we just run the MLP classifier without setting some a given random state, then every time we will get slightly different results due to this random component. So we spoke about the tolerance before. We consider that we have rich convergence if the loss or score doesn't improve by at least a given tolerance. for a given number of consecutive iterations. If this doesn't happen, so if we keep the same loss or score, or the change is less than this tolerance in in a given number of iterations, then we consider that we have reached convergence and we stop with the training. Again, if we this could take a very long time, so we could stop the training earlier if we said that we want to do at most a given number of iterations, 200 here, but we could increase or decrease this, and then we will stop training even if this condition here is not met. And then we could choose to print progress messages to the standard output so that we can see how the training works. So we can use the same classifier multiple times. If we set this warm start, so the same classifier object multiple times, and we could, if we set this warm start parameter to true, then the solution to the previous call, so to the previous time with fit this classifier can be used as initialization. And if we set it to false, then we just erase the previous solution and we start training from 0 again. Then we have some other parameters that customize the solver, so give different parameters that the solvers can have, such as the momentum and Nestero's momentum. And then we can also set another condition for early stopping. So we use this early stopping if we want to terminate training when the validation score doesn't improve. If this is set to true, then we will use 10% of the training data as validation and terminate if this score doesn't improve for a given number of iterations. If this is false, then we just use the tolerance condition here and this max iter condition here to determine when to stop. Then if we want to use early stopping, then we said we want to use part of the training data as validation. By default that's 10%, but we can change it using this validation fraction parameter. Then again, we have some other parameters that are used in the solver, such as beta 1 and 2, and this epsilon here. And then we have the parameter which tells us how many iterations without change we want to track. So here in the tolerance we said if the loss of score doesn't improve by a given number of iterations, then we can consider that we've reached convergence. And we set that number of iterations here in the a number of iterations with no change parameter, which is 10 by default, but again we could make it larger or lower if we want. And this is another parameter used in one of the solvers. So here we can see that we have a large number of parameters, but the ones that we're going to focus on in this course are going to be the hidden layer sizes, the activation function, the initial learning rate, and possibly we'll just mention the maximum number of iterations as well. However, all of these can be used and changed to get better results.